So far we talked about sets as kind of static collections of objects themselves. But sets can be used to construct all sorts of things. We already constructed relations out of sets, and we will talk more about that a little bit later. But one thing that we could talk about in a language of sets is something that you might be already familiar in a different context: functions. So what is a function if we are talking about it sets theoretically? A function is a special kind of relation such that everything in the first set, in the relation the set X, is related to only one, at most one, thing in a set Y. So, for example, here the first picture shows a function because everything out of 1, 2, 3, and 4 is connected to at most one letter on the right side. 1 and 4 are connected to letter A, 2 and 3 are connected to letter B, but it's not like the second picture when you have 3 connected to both A and B. Well, this is still a relation, but that would not be a function. So sometimes people talk about functions as mapping. You give the mapping something, some element of X, and it has to be able to tell you what is the element, what the corresponding element of Y is, or sometimes it might say there is nothing in Y that corresponds to this element. But at the very least, it shouldn't start telling you all sorts of different answers when you give it the same question. So here is some notation. So usually when we talk about functions, we don't write them as relations. We use the standard f of x equals y notation. And again, we can do it because we know that if we give a machine for f an element x, it will give us at most one element y. It may say there is nothing, but if it gives us something, it will give us something specific, something unique. And we call such element y that f would give us if we give f an element x, an image of x. So we talk about a function being from one set to another set, taking elements of a set x and mapping them to elements of the set y. And the set x is called the domain of the function, and y is called the codomain of the function. All it is just f takes elements of x and give us something in the set y. A range of f, or an image of the whole big set X under f, is all the y's that have something mapping to them by that function f. It could be that some things are not being mapped, but it could be that everything is mapped. And finally, a pre-image of a given element of y is the set of all x's that map into this specific y. And it's not required in general to be a set containing a single element. It can be a set containing multiple elements. So for example, in the function r, the element b has two things, 2 and 3, mapping to it. So the pre-image of the element b will be 2 and 3. So there are lots more definitions, and here a lot of different types of functions. And the ones that you are probably going to see most are the following. So if you have a function, that function is total if everything on the left side maps to something on the right side. So it's sort of so before we said that everything on the left side maps to at most one item on the right side. If the function is total, it maps to exactly one item on the right side. So we cannot have 1, 2, 3, 1 mapping to A, 2 mapping to B, and 3 just sitting there. If you give 3 to a function, it will say, sorry, there is nothing there. So more familiar examples, more numerical ones, is that if you take f, which takes integers to integers, and f takes number x to x plus 1, that's a total function. To any integer, you could add 1 and still get an integer. But if you take a function which is 100 divided by x, well, that's very much not a total function for integers, because you could divide 100 by 5 and 2 and 10 and 25 and get an integer, but for pretty much anything else, well, you also can divide it by -1 and stuff, but for pretty much anything else, you're not going to get an integer. Even if you switch to real numbers, well, if your x is 0, you cannot divide 100 by x, so it still would not be a total function. So a function that's not total is called partial. So other types of functions, which are sort of mirror images of those, are onto functions and one-to-one functions. A function is onto means everything on the right side has something mapping to it. So it's kind of a mirror image of a total. In a total, everything on the left had a line coming out of it. For the onto, everything on the right has a line coming into it. Similarly, kind of a mirror image of being a function is a function that's one-to-one. One-to-one means that everything on the right side has at most one line coming into it. Just like something is a function if everything on the left side has at most one line coming out of it. And the more special kind of functions are the ones called bijection, where everything on the left side has exactly one corresponding thing on the right side. Those are the nicest kinds of functions, and we will use them later on. So, for example, f of x equals x plus 1 is a bijection. Actually, it's not just over integers, over real numbers. Pretty much any class of numbers you take, this will be a bijection. So why do we need to know those things? Well, because we want to do things with functions, and some things we could only do if the functions are from a certain type. For example, as we said, being one-to-one is kind of a mirror image of being a function. And here's where it comes handy. If your function is one-to-one, that is, everything on the right has at most one line coming into it, you could reverse the direction of those arrows and still get a function. And this is called an inverse. So a function is a function, the inverse function f written as f to minus 1 is an inverse of f if it takes y to x as opposed to x to y. And if you give it a y, it tells you an x that the y came from if you applied f to x. So for example, if f takes 1 to a and 2 to b, then its inverse will take a to 1 and b to 2. It will tell you the single because it's a one-to-one function, because f was one-to-one function, the single element in the pre-image of the corresponding y. So one more thing that we could do with functions, at least if their domains and codomains match correctly, is compose them together. And this is something that you've seen before. When you apply one function, then you apply another one, then you apply maybe a third one. And here we call it a composition. So you could only compose functions f and g if the codomain of F is the domain of G. So F takes elements of X to elements of Y, and G has to take elements of Y into the elements of Z. So the order in which you're doing those operations matters. Sometimes all of those domains and domains and codomains are the same, integers to integers to integers, or reals to reals to reals. But still, if you take a number and first apply F and then apply G, you may get a different answer. So here's one example. Suppose f of x is x divided by 5, and g of x is ceiling of x, which means it's x rounded up to the nearest integer. If we take g of f of x, we will first take x, divide by 5, and then we take the ceiling, rounded up to the nearest integer. If we take f of g of x, then we first take the ceiling of x, and then we divide the resulting number by 5. And here is the difference. In the first case, we get the number 3 if we apply it to the number 12.5, because 12.5 divided by 5 would be 2.5. We round it up, we get a 3. In the second case, we round up 12.5, we get 13. Divide 13 by 5, we get 2.6. So order in the composition really makes a big difference.